Hi, today I'm going to be going over my analysis of project one. So question number one is asking us to estimate the moment of inertia about the X, Y, and Z axes. And so I included a diagram of the CubeSat. So the CubeSat is a nanosatellite and has an approximated mass of 7 kilograms. The dimensions of the CubeSat are in standard dimensions at 2U, which means that it's 10 centimeters by 10 centimeters by 20. And in order to estimate the moment of inertia, we need to derive an equation for the inertia. And since this is like a rectangular volume figure, it's going to be different than the typical moment of inertia equation. So that's why we have to derive it. So here I draw like the CubeSat and my coordinate system. I define my variables, X, Y, and Z, and then M for mass. And so then I continued to derive my moment of inertia equation from the momentum equation, and also I first used S in place of X, and then I changed it to X later on in a derivation. So after going through this with various integrations and canceling out some variables, I got to the equation of inertia equals 1/3 the mass times x squared plus xy plus y squared. And so then I plugged in my values. So I got I equals 1/3 times 7 kilograms times 0.1 meters squared plus 0.1 meters squared plus 0.1 meters squared. And so I got a moment of inertia of 0.07 kilograms times meters squared. So the second question is asking us to design a compact reaction wheel that will apply the proper amount of torque to rotate the nanosatellite at an angular acceleration. And the torque that is applied to the nanosatellite is directly proportional to the calculated moment of inertia. So as done above, this is the equation for the calculated moment of inertia. And we also know this relationship where angular displacement is just theta radians. This is supposed to say velocity. Angular velocity is the derivative of theta over the derivative of time. And then the angular acceleration is represented by the derivative squared of theta over the derivative of time. So we get a unit of radian per second squared. And so then I calculated the angular acceleration and also the angular velocity. So for the angular velocity, since it's asking us to rotate it at from 0 to 90 in 45 seconds, I got an angular velocity of 2 radians per second. And then for the angular acceleration, I got 0.04 radians per second squared. And since we know that torque is equal to moment of inertia times angular acceleration, we can plug in those values. And I got a torque value of 0.028 newtons per meter. And so according to the calculation, the torque needs to be applied in order to result in the indicated angular acceleration. The torque should be at around 0.0028 newtons per meter, which is what we calculated above. And so I said that the most common material for satellite would be aluminum. And this is the case because aluminum is a durable and light material that is pretty affordable to manufacture compared to other things like titanium. And so I was kind of unclear on this part of the project. So I said that the design of the compact reaction wheel would be rotating on the XY axis because that's what I've been calculating and working with, and with the moment of inertia derivations. And I also predicted that the shape would be like a thin circular disc. And since it has to fit inside the satellite, I decided to say that it would be 0.75 meters and mass of 10 kilograms, since I wasn't sure how to calculate those. And so the moment of inertia is calculated to be 1.40625 kilograms per meter squared. And I used the moment of inertia equation for a circular figure, which is 1/4 times mass times radius squared. And so I got this value. And so as I also said above, the compact reaction wheel should rotate on the XY plane in order to generate enough torque force to rotate the nanosatellite. And so I already did this calculation, but when assuming linear acceleration during all periods of the maneuver, the angular acceleration needs to be at a certain threshold to rotate the satellite from rest by 90 degrees, about the x-axis, in 45 seconds. So according to the calculations above, the angular acceleration would need to be at 0.04 radians per second squared. And so I did a graph. I am not sure if this is completely right. I wasn't super clear on what that question was asking. And then, so the maximum power of the motor for this model can be described by the equation that relates the power of the system and the torque of the system and the angular velocity. So I found this equation after doing some research. So power equals torque times angular velocity. So the torque is 0.0028 newtons per meter, and the angular velocity is 2 radians per second. So I got the power is 0.0056 watts. Right, thank you.